Scientists have discovered something truly remarkable about the deep interior of Earth. At the very center of our planet, where pressures and temperatures are unimaginably extreme, matter may exist in a strange state that is neither fully solid nor fully liquid. This unusual form of matter is called a Superionic state, and it could finally explain mysteries that have puzzled scientists for decades about how Earth's inner core behaves. For a long time, people imagined Earth's core in a very simple way: a solid metal ball at the center, surrounded by a sea of molten metal. While this basic idea is still mostly correct, new evidence shows that reality is far more complex and fascinating. The inner core may not be a hard, rigid solid like steel. Instead, it might be soft, flexible, and dynamic, more like warm butter than frozen iron. This discovery matters because Earth's core plays a major role in shaping the planet we live on. It influences earthquakes, volcanoes, and even Earth's magnetic field, which protects life from harmful radiation in space. Understanding what is happening inside the core helps us understand Earth itself and even other planets like it. No human has ever drilled anywhere close to Earth's core. The deepest drill holes reach only a tiny fraction of the distance needed. So how do scientists know what lies thousands of kilometers beneath our feet? The answer comes from seismic waves, which are vibrations created by earthquakes. When an earthquake happens, waves travel through Earth in all directions. These waves move at different speeds depending on the material they pass through. Some waves travel through solids only, while others can move through liquids. By measuring how fast these waves travel and how they bend or slow down, scientists can map Earth's internal layers. This method has revealed four main layers: the crust, the mantle, the outer core, and the inner core. The outer core is liquid metal, while the inner core has long been thought to be solid. However, there has always been a problem. Seismic data shows that shear waves, which only move through solid material, travel unusually slowly through the inner core. This suggests that the inner core is solid, but not a normal solid. Something strange is happening there. In everyday life, solids are rigid. Steel beams, rocks, and ice resist being bent or squeezed. But the seismic signals from Earth's inner core suggest it behaves differently. Measurements indicate that it is surprisingly squishy, meaning it can deform more easily than expected. This softness is measured using something called Poisson's ratio, which describes how a material changes shape when squeezed. The values seen in the inner core are much higher than those of ordinary solid metals. This raised an important question. How can the inner core be solid and yet behave like something partially liquid? For many years, scientists proposed ideas involving crystal alignment, melting boundaries, or strange iron structures. None of these explanations fully solved the mystery. The idea of a Superionic state offered a promising solution, but until now it was only a theory. To understand a Superionic state, it helps to think about how atoms behave in solids and liquids. In a normal solid, atoms are locked into place in an orderly pattern called a crystal lattice. They vibrate, but they do not move freely. In a liquid, atoms move around freely, sliding past one another. A Superionic state is a rare and unusual combination of both. In this state, one type of atom stays fixed in a solid structure, while another type moves freely like a liquid. The material is both solid and liquid at the same time. In the case of Earth's inner core, the solid framework is made of iron atoms, while lighter atoms, especially carbon, move through the structure like a fluid. This movement dramatically reduces the material's stiffness, making it softer and more flexible. Earth's core is mostly iron, but it is not pure iron. Scientists believe it contains small amounts of lighter elements such as carbon, sulfur, oxygen, hydrogen, or silicon. These elements help explain why Earth's core is slightly less dense than pure iron would be. Carbon is especially important because it fits easily into iron's crystal structure and becomes mobile at high temperatures. Under the extreme heat of the inner core, carbon atoms can break free from fixed positions and start moving, even while iron atoms remain locked in place. This movement of carbon atoms is the key to forming a Superionic state. It allows the material to flow and deform without fully melting, creating the strange properties detected by seismic waves. In 2022, scientists suggested that a Superionic iron-carbon alloy could explain the strange seismic signals coming from the inner core. But theory alone is not enough in science. Experimental proof was needed. The challenge was enormous. Earth's inner core exists at pressures up to 360 gigapascals and temperatures of 6,000 Kelvin conditions, far beyond everyday experience. Recreating this environment in a laboratory is extremely difficult. That is where a powerful technique called dynamic shock compression comes in. To simulate inner core conditions, researchers used a device known as a two-stage light gas gun. This machine fires tiny projectiles at incredibly high speeds using gunpowder and compressed gas. In the experiment, a small piece of iron-carbon alloy was launched at more than 7 kilometers per second faster than a bullet into a lithium fluoride target. When the projectile hit the target, a powerful shock wave traveled backward through the metal sample. This shock compressed the alloy to pressures of about 140 gigapascals and heated it to nearly 2,600 Kelvin. While this is still less extreme than Earth's inner core, it is close enough to reproduce the key physical behavior scientists wanted to study. The extreme conditions lasted only a few millionths of a second, but that was enough time to measure important properties using lasers and ultra-fast sensors. The results were striking. Under these conditions, the iron-carbon alloy showed very low resistance to shear waves, matching what scientists observe in Earth's inner core. This confirmed that the material behaves like a soft solid rather than a rigid one. At the same time, the iron atoms stayed arranged in a solid crystal structure, proving the material was not fully melted. Meanwhile, the carbon atoms became highly mobile, flowing through the iron lattice like people moving through a crowd. This combination of solid structure and liquid-like motion is exactly what defines a superionic phase. For the first time, scientists had experimental proof that such a state could exist under inner core-like conditions. The discovery solves several long-standing puzzles about Earth's interior. It explains why shear waves slow down in the inner core and why the material appears unusually soft. It also helps clarify why seismic measurements sometimes behave inconsistently when passing through the core. Instead of imagining the inner core as a frozen metal ball, scientists can now think of it as a dynamic, partially flowing system. This new model fits the data far better than older ideas. Earth's magnetic field is generated by the movement of molten metal in the outer core. However, the inner core also plays an important role by influencing heat flow and electrical conduction. If light elements like carbon are mobile inside the inner core, they could affect how heat and electricity move through this region. This may help explain changes in the magnetic field over time, including pole shifts and fluctuations in strength. Understanding the superionic nature of the inner core could therefore improve models of how Earth's magnetic field forms and evolves, something crucial for understanding both Earth's past and its future. Earth is not the only planet with a metal core. Mercury, Mars, many rocky exoplanets also have iron-rich interiors. If superionic states occur in Earth's core, they may exist in other planets as well. This discovery helps scientists understand how planets cool, generate magnetic fields, and evolve over billions of years. It may even help identify which distant planets could support life, since magnetic fields help protect atmospheres. The most important outcome of this research is a change in perspective. Scientists are moving away from the idea of the inner core as a static, unchanging object. Instead, it is now seen as active, flexible, and alive with motion, even though it remains solid. This discovery, published in National Science Review, represents a major step forward in Earth science. It shows how creative experiments and bold ideas can reveal secrets hidden deep within our planet. In simple terms, scientists have discovered that Earth's inner core may be made of a strange, hybrid form of matter. Iron stays solid, but lighter elements like carbon move freely inside it. This makes the core soft, flexible, and dynamic, explaining decades of confusing seismic data. Although we may never physically visit Earth's core, discoveries like this bring us closer than ever to understanding what lies beneath our feet. The heart of our planet is not cold and lifeless. It is active, mysterious, and full of surprises.